Hello everyone. Today we're diving into eigenvalues and eigenvectors, a key topic in the IBA IHL course, specifically topic 1.15. Let's get started. To understand today's topic with ease, you should have knowledge about matrix multiplication, calculating the determinant of a 2 by 2 matrix, and finding the roots of quadratic equations. First, I should introduce the definitions of eigenvalues and eigenvectors. A is a 2 by 2 matrix, and if X is a 2 by 1 non-zero vector and lambda is a constant. If we can find a vector X and a constant lambda that satisfy the equation A times X equals lambda X, then lambda is going to be an eigenvalue of the matrix A and X will be its corresponding eigenvector. Now, I will show you how to use the equation to find the eigenvalues step by step. To solve the equation for the eigenvalues, we should collect all terms on the same side. As you can see, X is common in both terms, so we can factor X out as a common factor. According to the definition, X is a non-zero vector. This means X does not make this equation equal to 0. So, the expression inside the bracket must be 0. But don't forget, the expression is a matrix, so its determinant can be 0. The solutions of the determinant are the eigenvalues of the matrix A. To figure out the eigenvalues, we first need to define the characteristic polynomial. As we have mentioned, the characteristic polynomial is equal to the determinant of the matrix expression, which is in terms of lambda. I would like to clarify that lambda is a scalar product, so lambda times the identity matrix looks like that. Now, I will solve a question that will teach you how to find the characteristic polynomial, calculate the eigenvalues, and determine the eigenvectors of matrix A. Part A of the question asks us to find the characteristic polynomial. For this, first, we should plug the given matrix A into the function. Then, we need to subtract the two matrices to simplify the expression. In matrices, absolute value notation denotes the determinant of the matrix. We can use this notation instead. You don't need to write the determinant anymore. To write the characteristic polynomial, we need to find the determinant of the matrix. I would like to remind you how to calculate the determinant of 2 by 2 matrix right now. We can easily define it as the difference of the cross product of numbers. Using the formula for the determinant, we can find the characteristic polynomial. After performing the calculations, we will obtain the characteristic polynomial. Now part B asks us to find out eigenvalues of the matrix A. When the characteristic polynomial equals 0, the roots of the equation are the eigenvalues of the matrix A. To find the eigenvalues from a quadratic equation, we should know either how to factorize it or how to apply the quadratic formula. Obviously, there are two options, either lambda minus for equals to 0 or lambda plus 3 equals to 0. There are two options, lambda might be 4 or -3. It means the eigenvalues are 4 and -3. If matrix A times vector X equals lambda times vector X, then according to the definition, lambda is regarded as an eigenvalue and vector X is its eigenvector. 2 by 1 vector X is defined by letters A and B. Lambda times identity matrix minus A equal to lambda, -3, -4, and lambda minus 1, times vector X equal to 0. Our equation is ready to find out eigenvector for each eigenvalue. If lambda equals 4, substitute 4 for lambda. I will get this 2 by 2 matrix. From here we will multiply these to matrix. Actually, just we need to multiply first row by first column. So for A minus 3B equals 0. You don't need to multiply the second row. because we will find similar equation. We will get the parametric solution because there's one equation but two unknown variables. Parametric solution means there is no exactly one answer for A and B. I will use the coefficient of B to define the EY, so A equals 3t. B automatically is going to be for t. Then substitute 3t and 4t for A and B, respectively. So x is going to be 3t for t. T is a common factor, it means I can take it out. We finally find out eigenvector for eigenvalue equals 4. We will use same method to find out second eigenvector for second eigenvalue, which is -3. Just substitute -3 for lambda. Then multiply first row by first column like we did before to find the first eigenvector. Then we get -3a equals 3b. If a equals to just t, b will be -t. Second eigenvector become t and -t. Since t is a common factor, I can factor it out to finalize my work. I hope you like the video. In the following video, I will mention applications 2 powers of 2 by two matrices.